In this video, we'll look at uncertainty and feature extraction. So as the robot is moving around, it needs to localize itself. So it needs to know where it is in the environment. It has got information from its internal sensors for depth reckoning. It's got its sensors, which is mapping the environment. And it's also got a built-in map. And it can combine all this information to try and work out where it is. The problem is that all of this different data information has got errors associated with it. So we need to consider this uncertainty before we can combine all this information. So we'll firstly look at what we mean by uncertainty. When you take a measurement of something, then you assume it's going to be right as you take the measurement. However, if you have lots of people taking that measurement, the chances are they will each take a slightly different measurement. So person 1 might take a measurement and get a value of row 1. Person 2 might take a measurement and get a value of row 2. The true measurement, EX, what we'd like to know, the exact value of that measurement, is going to be a combination of all these different measurements we've taken. So what we can do is we can plot this out and say, for example, we want to measure the length of this table up here. The first person takes a measurement and gets 102 centimeters. The next person takes a measurement and gets 103 centimeters. The next person takes a measurement, gets 102 centimeters, etc. If we build up a histogram of this, we will get a plot that might look something like this. So everybody's got slightly different measurements, but the majority is going to be somewhere in the middle. So what we can do is we can essentially plot up all these different measurements and we get a plot that looks like this. If we normalize this, so we normalize it by dividing by a value that gives us an area under here equal to 1. Then we've got a normalized plot, and this is what's called a probability density function. So we've got our measurements, our range of measurements along here, and the chance of taking a measurement at any particular value is the probability at that point. So as you can see, most people have taken a measurement at this value. Only a few have taken a measurement at this value here. A few more have taken here. What we can do is find the average of all this and find a mean value here. And this mean value is our best estimate of that measurement. So in terms of statistics, we want to find the mean of that. So the mean is essentially adding up all the values and dividing by the number of measurements. Alternatively, another way of looking at it is to look at each value and the probability of that value and performing that integral. So our mean measurement is the integral over all our different measurement possibilities, x, times by the probability of taking a measurement at that value. The variance is essentially the scatter in the data. So the variance is essentially how wide this peak is. So the wider it is, so if we had a very flat peak, so there's a lot of scatter in, that would have a large variance. A very sharp peak would have a very small variance. And we calculate the variance by looking at each value, or the difference that each value has from the mean value. So we're looking at that difference. We square it. If we just looked at the difference, then that would sum to 0. So we look at the square of the difference. So everything adds positively. So it's that difference times by the probability at that point, integrated. And then that gives us our variance. If we square root the variance, what we get is the standard deviation. So the sigma, the standard deviation, is the square root of the variance. And this is typically what we'd use on a calculator if we had a list of values, we'd find the mean and the standard deviation. So let's look at an example. We've taken 5 measurements of something, 1, 2, 2, and 3. If we add all them up, we can see the average is going to be 2, and then there's a value for the standard deviation. We'll just use the formulas we've just described. So our mean is we've changed from an integral into a sum because we're doing this discretely. Our values of x times the probability of that. Well, 60% of the time we've got a 2, 20% of the time we've got a 1, and 20% of the time we've got a 3. So it's 0.2 times 1 plus 0.6 times 2 plus 0.2 times 3, and that gives us our mean of 2. Similarly, for the variance, we have 1 minus 2 all squared times by the probability, so that is 1 squared times 0.2. 2 minus 2 all squared times by 0.6, which is this term, and then 3 minus 2 all squared times by 0.2, which is this. So we get a variance of 0.4, or standard deviation of the square root of 0.4. So that's what we'd do to find how confident we are in a value. We can take multiple measurements, see what the mean is, and that's our best estimate of that measurement. And we can also do a standard deviation or variance to see how much variation there is in that measurement, and therefore that gives us an indication of what the possible error is in that measurement. The problem in practice is we kind of take lots of measurements in order to get this plot. Okay, so this takes a lot of measurements to get a nice detailed plot like that. However, in most cases, when we do measurements, it'll follow a normal or Gaussian distribution, which is this shape. So any measurement we take will probably have a distribution of this form. It's symmetric, so the mean is the center value, so that's our average value. And it's got a certain width to it, which is a standard deviation. So for the Gaussian distribution, one standard deviation accounts for 68% of the area, so approximately 2/3. So within that one standard deviation, that is 2/3 of the area. If we go for 3 standard deviations, it is 99.7% of the area. So we're looking at this point here and this point, and within that area, it's 99.7%. So if we had a value, so first of all, if we measure something and say the average is, say we've got an average of 100, so we'll say that is our mean, and our standard deviation, sigma, so our mean is 100 and our standard deviation is 3. If somebody takes a measurement of this, then the value is 100, but 2/3 of the time they're going to get a measurement between 97 and 103. If we go for 3 standard deviations, that is going to be 91 to 109. So 99% of the time they take that measurement, they're going to get a value within that range. Whereas 2/3 of the time they're going to get a measurement within that range. So what we use our mean value as our best estimate of a measurement. We use the standard deviation to give us how confident we are in that measurement. Okay. So that's just a little bit of statistics, and we'll use that when we come to trying to work out where the computer is. We need to know how confident we are in our value of our measurement, and we can use the standard deviation value as a gauge or a value on how confident we are in that value we are using. So now we'll move on to feature extraction. So we discussed sensors in yesterday's work, and for example, we discussed the LiDAR, and we used the LiDAR to measure a range of something, or a range of an object. So that's telling us distances to objects, but it's not actually telling us anything about the object. So what we're going to try and do now is use that data to work out some kind of features or some kind of descriptors for that object. So let's imagine that we have a LiDAR sensor taking a measurement of a wall. So I'll just discard that for a second. So we have our robot here. So we have our robot. So we'll have a differential drive robot. We'll put our LiDAR sensor on the top, and it's taking distance measurements, and we've got a wall here. So it's going to take distance measurements, and it's going to do a measurement here, a measurement here, a measurement here. So it's doing various measurements. So we've got these individual measurements. So we've got at an angle of thigh 1, we've got a range 1, at an angle of thigh 2, we've got range 2, etc. So we've got a series of discrete points, but what we'd like to know is that this is measuring a wall. So what we can do is take that data and fit a straight line to that data. So there's our data points. And what we do is we fit a straight line to that. Down there. Now you're probably very familiar with fitting straight lines to data in Cartesian format, y equals mx plus c. So that's how we typically fit a straight line to data. In terms of our LiDAR, we actually do measurements in terms of polar coordinates. So it's a distance and an angle. So it makes more sense for our LiDAR to continue working in polar coordinates. So rather than y equals mx plus c for our straight line, we'll represent that in a polar coordinate form, and that is our equivalent straight line in polar coordinates. So our rho is our distance measure. Our rho is our distance measurement for each point. Our theta is our angle measurement for each point. And then these lead to having a straight line here defined by this perpendicular distance r. So r is the shortest distance to this line from the origin. And this forms a perpendicular there. And the angle that line subtends with the axis is alpha. Okay, so normally we think of y equals mx plus c, where we have an x and y values, and we determine the gradient and the intercept with the y-axis, and that's our normal straight line. In this case, our rho and our theta is our xy values, and our m and our c have now become our r and our alpha values. So it's the same principle, just in a different coordinate system. Now we'd like all these points to be exactly on this line, and then that will make putting a line through this very easy. We just draw it straight through. In practice, all our measurements are going to have a slight error. So as we said, if it's got a variance of say for example 3 millimeters, or a standard deviation of 3 millimeters, 2/3 of our measurements are going to be within 3 millimeters of this distance, but then 1/3 of them are actually going to be greater than that. Okay, so we're not going to get all our points exactly forming a straight line. We're going to get some scatter like that. And what we need to do is try and work out what is the best line through this data. So rather than have our equation that equals 0, what we actually have is this equation equals our point with some error associated with it. In order to find the best straight line through that, what we can do is define a function s, where s is the sum of all these values. So all these errors, it's the sum of all these errors squared. So if we put our formula in, it comes out to be that. And then if we want to minimize this, so we want to minimize how far all these points are away from the line. So for example, if we drew a line there, all these points are a long way away. Whereas if we draw a line here, these points are closer. So if we define a line that minimizes all these distances, then what we're saying is our function s, or ds by dr and ds by d alpha, has to equal 0. So that is the minimum point at which our values of d are closest to the line. So we can perform this differentiation and solve this, and we get an equation differentiating this with respect to alpha and then differentiating with respect to r and solving. We get two equations that tell us what our values of alpha and r have to be in order to get this best fitting line. Now I won't go into details of that. What you get out is a long formula, and the solution is in SIGRAD, so you could program it in. So I'm not too bothered about the actual exact equation for this module. That's just something you can copy from the book. It's the principle that counts. So what we're going to do in this module is do this procedure graphically. So let us say we've taken, these is our LiDAR measurements. So different angles of our LiDAR, we're getting these ranges. And we want to find the best fitting line through this. So what we can do is we can plot these up. So we plot the points up, draw a line through there. And then for now we'll just estimate by I. And this looks like it's the perpendicular here going there. We do a measurement and we find it is 310. So I equals 310 and our angle is 33 degrees. So for that, our R is, we said 310. And our alpha is 33 degrees. So what we've done is we've taken our individual data and we've made it into a feature. So we've gotten all these individual data points and made it into something defined by a feature. Now that feature is defined by two values: a distance measurement and an angle measurement. Okay. Now what we'll do is we'll get multiple features. We'll take measurements in an environment and we'll get potentially same features being measured and potentially different features being measured. So if I just escape that for a second, I will show you what I mean. So we go back to this scenario. So say we have our robot here taking the measurements, and we've got a wall here. So we've got a wall, we might have a cupboard on that wall, we've got that, and then the room goes like that. So we take some measurements, we take a measurement there, a measurement there. I'll do 6 measurements on here, for example, 3 measurements on there, 3 measurements on there, and 3 measurements on there. What we can do is, if we take all them points and draw a straight line through, we'd get a line that looks something like that, which makes no sense at all. So what we do is we group these measurements, and we'll group them in 3, for example. So we'll take that group of 3, that group of 3, that group of 3, that group of 3, and that group of 3. For them 3 points, we'll work out a straight line through there. So we'll take them 3 points, do a straight line, and then we'll work out our R and alpha for that line. So we'll do that for our first 3, so we'll call that 1. We'll do that for our next group, and we'll get a line looking something like that, and that is our R comma alpha for number 2. The same for this, the same for this, and the same for that. And what we'll find is for our 5 groups of measurements, we might get an R and an alpha that looks something like, for example, we'll have that as 2.1 and 20 degrees. That one will be 2.05 and 19 degrees. 3 looks like 21, looks like a similar angle, it's less distance, so that might be 1.1 meter. Number 4 is going to be something like 2.12 and 21 degrees. And 3 is something like 5.2 and 110 degrees, for example. So we've done our line fit and our sets of data and getting that out. So you can see you've got similarities. So 0.1, 0.2 and 0.4 have got very similar values here. So that means they are all measuring the same feature, which in our case is they're all measuring this wall along here. This set of data, which is group 3, is slightly different. So this is a different feature, and as you can see, it's the front of the cupboard. And number 5 has got different values, and this is actually another wall. So by looking at bits of the data at a time, extracting our R and alpha values, we can then match up to see which is the same feature. So for example, 1, 2 and 4 are all the same wall being measured, and which are different features. So that's what we've done here. So we've taken a few points at a time, worked out our R and alpha value, and then we're grouping together points that look similar. So when we group them together, we need to have a threshold. So what do we define as being close or being a match, and what's defined as a different object? So we need some kind of threshold value to make that decision. But if we take our R and alpha values, so for example, in this case, we might have taken, say, 21 measurements. We've grouped them into 3, so that's our first 3 measurements. And we're getting a value of R and alpha corresponding to that. Our next group of 3 measurements give these values. And what we can do is plot R and alpha in parameter space. So we're doing a plot of just R against alpha. So these are not physical locations. This is just looking at how R and alpha correspond to each other. And if we plot this out, plot R against alpha, what we find is we get a cluster of points here. We get a cluster of points here, and we get a point here. So from all that data we have measured, so from all the measurements, we've actually determined 3 features within the environment, which has got a characteristic R and alpha at these values. So this is what we mean by data extraction, is getting our individual data points and trying to interpret what is sort of the physical relevance of that within the environment. We'll come back a bit more into that in the next video about localization, so you'll see that working a bit more in practice. The final thing I want to discuss on this video is the error from odometry. So this will be a very quick mention, but as I said, when we're using sensors to measure a robot moving, there's problems with wheel slip, with bias on accelerometers and gyroscopes, that the error increases. So if you work through the analysis, so again, it's in Sigrid, the book, for more details. I just want to summarize it here. But if you work through it, what you find is due to wheel slip and that, if you try and track the motion of a robot so you know exactly where it is to start with, because you get these errors in these measurements, as the robot moves, you get an error in its X position and also in its orientation. And as you progress, with time and in distance, then this error gets larger and larger. And what you find is, if you do purely through depth reckoning, so purely using the optical encoders and the accelerometer, what you will find is the error in X, so the translational error increases. But what is a bigger problem is your rotational error. And because you're getting a rotational error in your robot, that then leads to an error in your Y coordinate, or your Y displacement of the robot. So this is why we have to use sensor data in order to help to reduce these errors in the odometry and sort of try and minimize them as we move forward. So in terms of our orientation in this error here, we could use a compass, which would then decrease this error because we know which way it's orientating. And there's methods for decreasing the error in the X value. Okay, so that's just something to bear in mind. As a robot moves, its expected location, or the error in its expected location, increases, and we need to account for that. So what we've done in this video is look at some errors, look at extracting data into features, and looking at how errors increase over time potentially. So what we'll do in the next video is bring all these ideas together and look at ways of using this data to try and reduce these errors building up as the robot moves.